So moving on with relativity, we're now going to calculate the momentum, mass, energy, and how to add velocities. So the classical expressions, if you remember from Physics 1, for momentum and for mass, they change when you go to a higher speed. So classically, the momentum we said was P equals mv, but now we need to change that because the mass effectively seems to change. So the relativistic mass, mrel, is the rest mass, m0, times gamma. So that's m0 divided by 1 minus v squared over c squared. And since gamma is bigger than 1, that means that the mass increases. So the faster something moves, the higher its mass is. And so the mass in the classical equation changes to gamma m0. And so the momentum increases faster than you would expect, doesn't go linearly with v. If you look at the picture there, you can see what that means is that as you go to higher and higher v, you approach the speed of light, and so we get close to 1 minus 1. 1 minus 1 is 0, and so we'd have gamma being 1 over 0, which is infinite. And so the mass of the object increases infinitely as you approach the speed of light, and that's the reason why you cannot get anything to move faster than the speed of light, because as you approach the speed of light, it gets heavier and heavier. You have to put more and more energy into it to accelerate it, and so it's just impossible to get it traveling as fast as the speed of light, let alone faster. The formula for energy also changes. Remember, classically, kinetic energy of something moving was just 1/2 mv squared. Relativistically, we have a more complicated equation, and it's the total energy, which is gamma m0c squared, minus the rest energy is equal to the kinetic energy. So the total energy minus the rest energy is gamma minus 1 m0c squared. And you can see the picture down the bottom of the classical expression for the kinetic energy. That's just a quadratic, kinetic energy goes as v squared. Relativistically, as you go closer and closer to c, gamma goes towards infinity, and so the kinetic energy goes towards infinity, which again, of course, is impossible. You'd have to put an infinite amount of energy into it to get it to accelerate to the speed of light. So that's why nothing that has a mass can travel at the speed of light. And you'll notice that in that equation for the total energy, we said the total energy was the rest energy plus the kinetic energy. So the total energy is gamma times the rest mass, m0 times c squared. So the total energy goes to infinity as v goes to c. But that rest energy, E equals m0c squared, that's the equation E equals mc squared that you always see when you see Einstein, right? So Einstein said E equals mc squared. So what that means is that any object, even if it's not moving, if it has a mass, it has an energy built into it. And we can get that energy out by using nuclear reactions. So the sun and nuclear reactors, nuclear bombs, what they do is they convert small amounts of mass into huge amounts of energy. If we want to come up with an equation that relates the energy and the momentum to each other, there's also another equation that E squared is equal to P squared C squared plus the rest mass squared times C to the 4th. And we're not going to use that very much, but we'll come back to it in later chapters when we talk about the momentum of light. So mass and energy are interchangeable is what the equation E equals mc squared means. So the basic result of special relativity is that nothing that has any mass can equal or exceed the speed of light, because this would require infinite energy, and that's just not possible. So let's do a few calculations. So what's the rest energy of an electron, which has a rest mass of 9.11 times 10 to the minus 31 kilograms? So rest energy is M0, 9.11 times 10 to the minus 31, times C squared. And C, remember C is 3 times 10 to the 8 meters per second. Okay, so we're going to multiply by 3 times 10 to the 8 squared. So that'll give us a big number. But because the mass is so small, we get 8.2 times 10 to the minus 14 joules, which is quite a small amount of energy. So normally when we talk about energies that are very small, we talk about them in terms of electron volts. So if you remember, the energy of electron volts was introduced probably back in module 2 when we were talking about voltage. So if you move one electron through a voltage of 1 volt, you get an energy of 1 electron volt, which is 1.6 times 10 to the minus 19 joules. So if I convert that energy from joules to electron volts, and we're going to do this a lot in the next chapters. So remember, when you do a conversion, you write a fraction. I want to get rid of the joules. So I'm going to put in the denominator so that the units of joules cancel out. So if I look at my equation, 1 goes with the EV. 1.6 times 10 to the minus 19 goes with the joules. And so I get an energy of 5.12 times 10 to the 5 electron volts. Okay, so it's 500,000 electron volts. Okay, so now let's look at an elementary particle called a muon. So if I have a muon that's moving at, that should say 0.95 times the speed of light, it has a rest mass of 1.9 times 10 to the minus 28 kilograms. And we want to know what's the relativistic mass, what's the momentum, what's the total energy, and what's the kinetic energy. All right, so I've got all the equations there, and you can see that they all involve gamma. So let's put in first our calculation of what gamma is. So gamma is 1 over the square root of 1 minus v squared over c squared. So that's 1 over the square root of 1 minus 0.95, c is my v, squared divided by c squared. And remember, when you do this, the c's cancel out, so you never have to put in that c is 3 times 10 to the 8, so 1 minus 0.95 squared. And I get my gamma is 3.203. So now I've got my gamma, I can start to put things into the equation. So remember, first thing, it wants relativistic mass. So relativistic mass is gamma times m0. So gamma is 3.203. m0 is 1.90 times 10 to the minus 28 kilograms. And so I get my relativistic mass is 6.09 times 10 to the minus 28 kilograms. So it's 3.2 times heavier than when it was stationary. Okay, next thing it wants is the relativistic momentum. So the relativistic momentum is gamma times the rest mass times the speed. So gamma is 3.203. The rest mass, 1.90 times 10 to the minus 28. So that's just going to be, that combination is just going to be my 6.09 times 10 to the 28 times my speed. Now my speed is 0.95 times c. So my speed is 0.95. And I have to multiply that times the numerical value of c, which is 3 times 10 to the 8. And I get 1.73 times 10 to the minus 19 And the units for that is kilogram meters per second. If you can remember from physics 1, it's mass times velocity. Okay, next thing, what's the total energy? The total energy is gamma times m0 c squared. Okay, so gamma times m0, that's just this again. Okay, so 3.203 times 1.90 times 10 to the minus 28 times c squared, 3 times 10 to the 8 squared, and I get 5.5 times 10 to the minus 11 joules. Okay, and finally, what's the kinetic energy? The kinetic energy is gamma minus 1 times m0 c squared. So gamma minus 1 times m0 c squared. So gamma is 3.203. So gamma minus 1 is going to be 2.203 if I subtract 1 from it, times 1.90 times 10 to the minus 28 times 3 times 10 to the 8 squared. So that's my c squared. And I get that my kinetic energy is less than the total energy. It's 3.77 times 10 to the minus 11 joules. Okay, so these are pretty straightforward calculations. Again, just remember it all hinges on being able to calculate gamma correctly. All right, so the last thing is relativistic velocity addition. So remember, we said nothing can travel faster than the speed of light. And so when we add two speeds together, they always have to give us a number that's less than or equal to the speed of light. So if you look at the example of the rocket that's firing a canister, so the rocket's traveling towards the Earth at half the speed of light, and it fires a canister towards the Earth at 3/4 the speed of light. So based on normal velocity addition, we'd say, okay, we just add a half plus 3/4, which would give us 1.25 times the speed of light. And of course, that's impossible. Okay, so how do we add those two speeds together to give us a number that's less than the speed of light? Well, we use the velocity addition equation that's over on the side here. So the numerator is our normal velocity addition. We just add the two speeds together. But in the denominator, we have a factor that's going to make it so that the sum of those is always going to be less than c. Okay, so we need to give these things symbols. So the speed at which the object is moving, that's our v. The speed at which the moving object fires the second object, that is the u prime. And you can see in the two examples, one, the u prime moves in the same direction as v. In the other, it moves in the opposite direction as v. And so if it's moving the opposite direction, we put a sign of minus. So u prime is negative 0.75 c. And u is the speed that's measured by the person on Earth. So the person standing on Earth measures the speed of the canister relative to it, and that is u. Okay, so let's do a calculation. So here we've got a spaceship that's leaving the Earth, or it's going past the Earth at 0.71 times the speed of light, and it fires a second stage that's at 0.87 times the speed of light with respect to itself. And we want to know what's the speed of the second stage with respect to the Earth, if it's fired in the same direction or if it's fired in the opposite direction as the spaceship. All right, so we've got v is the speed of the spaceship, so that's 0.71 c. And for the first part, u prime, the speed of the second stage, is going to be 0.87 c. In the part B, where it's moving in the opposite direction, we're going to just put minus 0.87 c. And we want to calculate what's u. So for A, all we're going to do is plug our numbers into the equation. So it's going to be v plus u prime over 1 plus v times u prime over c squared. So it's 0.71 c plus 0.87 c divided by 1 plus 0.71 c times 0.87 c divided by c squared. Okay, so if I look at this, let's see what we got. On the numerator, we're just going to add the two together. So I'm going to get 1.58 c. So if we were to add the two speeds together, we'd get something that's traveling about 1.5 times faster than the speed of light, which is impossible. In the denominator, now if I look, I've got a c times a c here, and that's going to cancel out with the c squared on the bottom. So I'm just going to have 1 plus 0.71 times 0.87, and that denominator there, that's going to be 1.618. So I've got 1.58 divided by 1.618. So it's going to be 1.58 c over 1.618, which is 0.977 times the speed of light. So it's getting close to the speed of light, but it's not there. All right, what if we fire it in the opposite direction? So u prime is minus 0.87 c. So now u is going to be 0.71 c minus 0.87 c over 1 plus 0.71 c times negative 0.87 c over c squared. Okay, so again, the c's in the denominator are going to cancel out. And I'm going to get in the numerator negative 0.16 c. In the denominator, I get 1 minus 0.618. And I get negative 0.42 times the speed of light. Okay, so again, the math is fairly simple. Just a matter of assigning the correct variables to the different speeds and then doing the calculations. So what I want you to do is to work through a number of problems. So for the first one, you're going to do something similar to what I did with the muon. You've got a proton, you're given its rest mass and its speed, and you want to find the relativistic mass, the momentum, the total energy, the rest energy, and the kinetic energy, and express those energies both in joules and also convert them to electron volts. Remember, 1 electron volt is 1.6 times 10 to the minus 19 joules. And for the second question, we have rocket A approaching the Earth at 0.7 c from the left, and rocket B approaching the Earth at a speed of 0.7 c from the right. We want to know at what speed does rocket A measure rocket B approaching it. So you're going to have to think about which is V, which is U prime, so that you can figure out what U is and make sure you get the signs correct.